Hello everyone, this is workshop 3, Deconstructing an Atom. Atoms are going to be one of, if not the most important particle that you learn about in your chemistry classes, and so it's important to understand how we define an atom, the parts that comprise it, and the theories that led up to our current understanding of how atoms exist in our universe. And so one of the first theories of how an atom looks comes from Thomson, Plum, pudding model. So, what Thomson's plum pudding model suggests is that atoms, as they existed, should have been some type of particle that has a largely positive charge itself, but then scattered throughout this positive center are little pockets or small negatively charged particles. And these will be what we know as electrons. So a positive center with small negativity scattered within it. Let me actually draw this a little bit bigger. So we have our positive particle, and we have our negative electrons scattered throughout the molecule, or the particle, scattered throughout the particle itself. And that's what gives its name, plum pudding model, because this looks similar to the actual dessert of plum pudding. A uniform particle with pockets of negative particles scattered throughout it. And this was how the atom was drawn for a long time, until we get then to Rutherford. And Rutherford is known for his gold foil experiment. In his experiment, Rutherford took a piece of gold foil and bombarded it with alpha particles. Alpha particles have a positive charge to them. And if Thomson's plum pudding model was how atoms looked in the universe, then hitting it with positively charged particles, you would expect them to go through the atom itself wherever there is a positive charge, because it's a positive molecule just with little pockets of electrons scattered throughout it. But instead, I'm going to do this in red just because this marker's dying a little bit. Instead, what happened was that the alpha particles hit the piece of gold foil, and while some particles kept moving in a straight line as expected, a lot of them deflected into different directions, and some even bounced back towards the source themselves. And so, if the particles are not traveling in a straight line and they're refracting in all different directions, the plum pudding model couldn't be correct. The atom had to look different than how it was originally described. And so what Rutherford proposed instead, which is now how we view the atom, is that atoms themselves are a positively charged nucleus. All of your positive parts of the atom are tightly bound together in one central nucleus. And surrounding said positive nucleus are the actual electrons. This way, when the alpha particles hit it, since the alpha particles do have a positive charge to them, some of them are able to pass through just fine, but a lot of them are going to interact with the surrounding particles and cause the actual bending that Rutherford saw. So, from Rutherford's gold foil experiment, we get Rutherford's theory about how the atom is structured, which is drastically different from the original plum pudding model. One, most of the atom's mass and the positive charge that it has come from a small core nucleus. Two, most of the atom's volume is empty space with tiny negative electrons dispersed throughout it. This is why some of the particles were still able to just pass through with no issue and not be deflected. And three, there are as many electrons as there are positive particles, so the atom is electrically neutral. If you have 6 positive particles, which are called protons, so if you have 6 protons and your atom is neutral, you have 6 electrons. And so based on his theory, we get the subatomic particles that make up the atom. We have protons, neutrons, and electrons. Protons and neutrons are going to be found in this small core nucleus. There you go. Small core nucleus. The neutron is actually going to be where most of our mass comes from. Neutrons and protons have roughly the same mass, but neutrons are still heavier. And so the mass of our atom is going to largely be derived from our neutrons in that small core nucleus, along with the mass of the protons added together. And then with the atom's volume being mostly empty space, that is where the actual electrons are going to reside. And you can see here, electrons are significantly lighter than protons and neutrons. They are not adding anything significant to the mass of the element itself. So while the nucleus is providing the mass of our atom, the volume, the actual space that the atom is taking up, is based on the electrons existing around that small positive center. And of course, then that third rule, that comes from the actual charges themselves. These charges are relative to each other, but protons are going to have a positive 1 charge and electrons are going to have a negative 1 charge. And that's why we only have to have as many electrons as there are protons to have a neutral atom. Neutrons are 0. And so as long as the number of electrons and protons are equal, your atom is neutral. The neutrons themselves are just there for the actual mass of the atom. And so if we know our 3 subatomic particles, we can use this to then write notation for our different chemical elements. So there are 2 types of notation that we're going to use when writing out our chemical symbols. Both are known as isotope notation, and this first one is going to have 3 parts to it. It's going to have the general form of A, Z, X. A is going to be your mass number, so that would be the sum of your protons and neutrons. Z is going to be your atomic number, and this is just the number of protons that you have. And X is going to be your chemical symbol. This is the 1-letter or 2-letter abbreviation for your chemical that you'll find on the periodic table. This is going to be the main notation that you're working with and the most common way that you're going to see it written. But there is another form of isotope notation that only relies on the chemical symbol and the mass number. And so that would be X-A. And in this case, X can be your chemical symbol, or it could be the full chemical name. But A is still your mass number. And so to use the first example, write the isotope notation for a neutral chlorine atom with a mass of 37. They're already telling us a lot of the information we need. We know that we are working with chlorine. On the periodic table, its chemical symbol is Cl. And they're telling us it has a mass number of 37, so it goes in the top left over here. And the last thing would then be to find chlorine on the periodic table and write its atomic number as it's listed there, which is 17. Or to use the other notation that we have, it would also be correct to say Cl37 or even chlorine 37. And from all these notations, we can figure out the number of subatomic particles that we have. If the atomic number is the number of protons, then we know, I'm just going to abbreviate protons as P with a little plus sign in the corner. The number of protons then has to be 17. If the mass number is the number of protons plus the number of neutrons, and I'll denote that with n raised to the 0, because charge is always going to go in your top right corner. If we have 17 protons and we know our mass number is 37, 37 is equal to 17 plus n, which means that the number of neutrons we have is 20. And now this element has no charge to it, it's a neutral atom, so we know it has to have equal number of protons to electrons. So if we have 17 protons, we also have, I'm going to denote this as E minus, we also have 17 electrons. Using the second example, how many protons, neutrons, and electrons are in uranium? I can write it over here. So 238. So U is going to be uranium. Again, we're going to look at the different parts that we have in our isotopic notation to know how many protons, neutrons, and electrons we have. Protons we get directly from the atomic number. So we currently have 92 protons. Neutrons is the difference between the mass number and the number of protons. So 238 minus 92. We have 146 neutrons. And electrons, again, this is a neutral atom. And so for our electrons, we also have 92. Now, I'm bringing up the fact that these atoms are neutral a lot because you're not always going to work with neutral atoms. In this case, we are neutral uranium, neutral chlorine. But there are different ways that atoms can exist. Sometimes you can lose electrons, sometimes you can gain electrons, and the same is true for our neutrons. Sometimes you can gain neutrons, sometimes you could lose neutrons. And so in both of those cases, the notation, the form of the notation will stay the same, but the number of subatomic particles you have are going to be slightly different. And so one that we have to worry about is an isotope. And isotopes are, I'm going to pull up the exact definition so I can write it out. But essentially, isotopes are taking the same chemical itself. So let's say chlorine, in this case, we have two molecules of chlorine, but one has a mass of 37, the other has a mass of 36. The number of protons cannot change. The protons tell you the atomic number. The atomic number is inherent to the actual chemical itself. If you change the number of protons, you are now changing the element that you're working with. And so for the mass to change, but the protons to stay the same, the number of neutrons then had to have changed themselves. We had to have lost a neutron in this case to go from 37 to 36. So isotopes, atoms with the same number of protons but different number of neutrons. And so if your masses differ but the elements stay the same, you're working with isotopes. And now, let's say again, we're bringing up chlorine, but now we have neutral chlorine versus chlorine minus. We said before, the way to have a neutral atom is to have equal number of protons and electrons. And so, if we go back with our original notation here, we know that this neutral chlorine atom has 17 protons, so it also has 17 electrons. But this chlorine is not neutral, it has a negative charge associated with it. It has that little minus in the corner. Because it has a negative charge to it, that means the number of electrons and protons are not balanced. There is a difference between the two. In this case, because it is -1, remember that electrons are negatively charged, so if the atom overall is negative, it has to have more electrons. Chlorine is still going to have 17 protons, but to have a more negative charge to it, it has to have 18 electrons. And then let's say you somehow have chlorine plus here. Again, the number of protons has to stay 17 for this to be chlorine. but now it has a positive charge, which means there are more protons than there are electrons. We have more positivity in our atom than we have negativity, so there has to be more protons. That means we lost one electron. So chlorine plus would have only 16 electrons. And these are what we call ions. And so it's again atoms with the same number of protons. That's not going to change unless you are changing your element. But now for ions, we have a different number of electrons. So the protons are inherent to the atom itself, but the neutrons and the electrons can vary based on the circumstances. For the isotopes, that is just a difference of mass. You can still have a neutral compound with your neutrons changing. You are just changing how heavy or how light it is. Ions can exist because the element is still staying the same. We still have 17 protons, but now you're giving it some type of charge. It is no longer electrically neutral, and it's going to have a slight negative charge to it or a slight positive charge to it. And now with our subatomic particles, we can write isotope notation for all different elements on the periodic table, all the different isotopes, and all of their different ions. So for our first set of problems, they want the isotopic notation of each element, the number of protons, neutrons, and electrons that there are, and the full name of each of these elements. And so we're going to start with the isotopic notation, but I'm also just going to call these by their full chemical names as I go along. So Au, that's going to be gold, Au2+. Gold is number 79 on the periodic table, so our atomic number is 79. And now for mass, a mass wasn't given to us, and so instead we're going to use the mass on the periodic table itself, but we're not going to use the decimals that are given in the masses, because that would imply that there is a fraction of a neutron or a fraction of a proton, and that is physically not possible. So instead, we're going to round to the nearest whole number. Let me write this a little bit bigger. And so if gold's mass is 196.97, I'm going to round that up to 197. So from our atomic number on the periodic table, we already know the number of protons to be 79. If our mass is 197 and we have 79 protons, we subtract the two, 197 minus 79, and we have 118 neutrons. And now for our electrons, we have to look at the charge of the ion itself. If it has a +2 charge, the positive charge means we have more protons than we have electrons. And we saw before that charge relative is either +1 or -1 for each of these. And so that means 2+, we have 2 more protons than we have electrons. So if we have 79 protons, we must have 77 electrons who have that +2 charge, those excess protons. And of course then this element is gold. So now P3 minus. Again, atomic number, periodic table. Phosphorus has an atomic number of 15, and its mass is roughly 31, if we estimate. And so number of protons is 15. 31 minus 15 tells us that there are 16 neutrons. Based on our charge, minus means that we have excess electrons, and 3 minus means we have 3 more electrons than we do protons. And so if the charge is negative by 3, we have to have 18 electrons to cancel out the charge of the 15 and give it a -3 charge. Ga3+, for us. So Ga 3 plus. Gallium is 31, yes, 31 on the periodic table. And its mass is roughly 70. So number of protons is 31. Number of neutrons, 70 minus 31. We have 39 neutrons. And electrons, we have a positive charge on our ion, so it has to have more protons than electrons. 3 plus means 3 more protons than electrons. And so we only have 28 electrons on gallium. I forget if gallium has 1 L or 2. I'm going to put 2. S2 minus. Sulfur is element 16 on the periodic table. Its mass is about 32. And so we know it has 16 protons. Mass minus atomic number, we have 16 neutrons. And if it has a minus charge, it has more electrons. 2 minus tells us it has 2 extra electrons to protons, so we have 18 electrons in our sulfur. Ag plus. I'm going to erase these down here for a bit just because I need to move them down, so I'll move them as I go. So Ag is silver. It's number 47 on the periodic table, and it has a mass of about 108. So we know the number of protons is number 47, which means then the number of neutrons has to be 61. 108 minus 47 gives us 61 neutrons. Positive charge, we have more protons. If you don't see a number next to the charge itself, that is just saying 1. So instead of writing the number 1, you just put plus or minus. Just like if you have an algebraic equation, you don't write 1x, you just write it as x. It's the same thing. It's the imaginary 1 that we assume is there. So there is 1 more proton than electrons. We have 46 electrons in silver. So F was bromine, nope, B, oh, so the bismuth, 3 plus. So Bi 3 plus. Bismuth is going to be number 83 on the periodic table, and it has a mass of about 209. So number of protons, 83. Number of neutrons then is 126. 209 minus 83. Number of electrons, positive charge, we have more protons. 3 plus, we have 3 more protons than we do electrons, so we have 80 electrons. W. Now G is Br, there we go. So Br minus. Bromine is number 35 on our periodic table, and it has a mass of roughly 80. So, number of protons is 35. 80 minus 35, we have 45 neutrons. Now we have a minus charge on our atom here, and so we are going to have more electrons than protons. it's just minus, so -1. We have one more electron than we do protons. We have 36 electrons. Last two. O2 minus. Oxygen has an atomic number of 8, and it has a mass of about 16. So that means we have 8 protons to work with on oxygen. 16 minus 8, we also have 8 neutrons as well. You'll notice with a lot of the elements earlier on in the periodic table, the number of protons and neutrons tends to be equal or like close to equal. And now for electrons, minus charge, we have more electrons than we do protons. 2 minus, we have 2 more electrons than we do protons. So we have 10 electrons on this oxygen. And I'll go back and write in the names once we are done with this last one. So last example, Al3+. So Al3+. Aluminum is number 13 on the periodic table. It has a mass of about 27. And so the number of protons is 13. 27 minus 13. The number of neutrons is 14. And the number of electrons has a our ion has a positive charge, so we have more protons than we do electrons. It has a 3+ charge, so 3 more protons than electrons, and so we have 10 electrons. And now just to quickly write in the names of the element. So silver, bismuth, bromine, oxygen, and aluminum. So, with isotopic notation, you are able to get all of your subatomic particles. Our atomic number gives us our protons. Our mass, when you subtract our atomic number, gives you your neutrons. The charge will tell you the number of electrons. All of these ions had charges. If any of these were neutral, your protons and electrons should be equal to each other. But either way, with notation, you're able to get the number of subatomic particles. And even if you are not given a mass, so long as you have a periodic table, which you will be provided, you can know the mass of the element when rounding, and you can get all the information that you need. Now, this last problem is asking for the same information as the last one, but now it is given to us in a table rather than... Now, this last problem is asking for a lot of the same information as the previous problem. We are just now working with a table rather than a right-now question. We need to know notation. We need to know our Z value and our A value. Remember our atomic number and our mass number. From all of our values, we can figure out protons, electrons, neutrons, the charge, and the name of the element itself. So, Z is always going to be your atomic number. You have to know that these letters are associated with the specific values. And so if Z is our atomic number, then we know part of our notation. We actually know a lot of our notation. The number in the bottom left is going to be 82. And now we just have to look for 82 on the periodic table itself, which is PB. So 82 PB. And now before, actually scratch what I said, what I was going to say, they also give us our mass number. So there is no math that we have to do yet. They already tell us the mass of this element is 204. Atomic number is 82. The number of protons is 82. There we go. And now the number of electrons is 80. We have 82 protons versus 80 electrons. And so there's a difference between our charges. We have 2 more protons than we do electrons, and so this isotope is going to have a 2 plus charge. Now to get our neutrons, again, subtracting mass number from atomic number. 204 minus 82, we have 122 neutrons. And from our difference in protons and electrons, our charge is 2 plus. And so Pb, that element is lead. Now for our second row, they're telling us the name of the element already, so we can put the symbol in our isotoping notation. Selenium is the chemical symbol Se. They're telling us our mass number, so we can put the number in the top left of our notation. And now they're telling us the number of electrons, the mass number, and the name. From the name, we can get the atomic number itself. Selenium is element 34 on the periodic table, which means we know our Z value, and that means we know our number of protons. And now neutrons, 79 minus 34, we are going to have 45 neutrons in this specific isotope of selenium. Once again, looking at our differences in electrons and protons, now we have 2 more electrons than we do protons. More electrons means we're going to have a negative charge, and since we have 2 more, this element is going to have a negative 2 charge. 2 minus to account for the difference in electrons, the additional electrons that we have compared to our protons. Third row, they tell us our mass number, the number of protons, and the number of electrons. Number of protons is the same as our Z value, our atomic number. So this is 33. Element 33 is AS. So AS sub 33. And they tell us our mass number is 75. And so we can find the number of neutrons. 75 minus 33. We're going to have 42 neutrons. And now notice, our number of protons and electrons are the same. We have an equal number of positive particles, equal number of negative particles. This element is not going to have a charge. And so there are 2 ways you can actually write this notation then. You can leave this as it is, just leave it as a neutral element, and this would be correct. But if you want to put a 0 up here as well, that would also be accepted. It's just the 0 is kind of not necessary. If you don't put a positive sign or a negative sign there, people know that you are saying that the element itself is neutral. So for our charge, 0. And so the last part, AS, that is the chemical symbol for arsenic. Fourth row, we know the number of neutrons, we know the charge, and we know the element that we are working with. If we know that we are working with tin, we can already put in our chemical symbol. Tin is the symbol Sn. Sn on the periodic table is number 50. So we have our value for the bottom left. We have 50 as our atomic number, which is also then our number of protons. And if we, I'm writing a little bit crooked. I'll fix this as well. But if we know that we have 50 protons, and we know that we have 67 neutrons, just like before when we were subtracting mass number by atomic number to get the number of neutrons, we can add together our number of protons to our number of neutrons and get our mass value. Our mass number is 117. And so the last part, knowing our number of electrons, we know that the charge is 4 plus. Positive charge, we're going to have more protons than electrons. 4 tells us that we're going to have 4 more protons than we do electrons, and so we have 46 electrons. To give our notation a 4 plus charge. And now last row. Oh, I'm sorry. This is a separate row from this one. So row, yeah, just want to make sure that was row 5. We know our Z value, we know our number of neutrons, and we know our charge. If we know our z-value, we know what element that we are working with. So actually we can write in our number of protons first. Z-value is 7, so we have 7 protons. It doesn't really matter which order you fill this in. I'm just going to fill in the protons first. By the way, 7 protons, atomic number of 7. We are looking at the 7th element on the periodic table, which is nitrogen. So we can fill in part of our notation here. N with a 7 in the bottom left. Number of neutrons is 7. So again, 7 plus 7. Our mass is 14. Last part is electrons. We have a 3 minus charge. Negative charge means we have more electrons than we do protons. And we have 3 more electrons than we do our protons, so we have 10 electrons to give this that 3 minus charge. And our last bit, I'm just going to move this over so it's in line with the rest of them. Now we have Xe 54, 131. So they only give us the isotopic notation. Atomic number, bottom left. So we have 54 as our z-value. Mass number, top left, so 131. If we know our atomic number, we know our number of protons. Based on the notation itself, there is no charge in the corner there. So the number of electrons must be equal to the number of protons to make this molecule, or sorry, make this atom neutral. And now, like we were doing before, mass value minus atomic value, mass number minus atomic number. 131 minus 54, we have 77 neutrons. Like we said before, no charge in the top right of our notation, so the charge is neutral, it is 0. And Xe is going to be xenon. So each row gave us different information about each element, and each row we were able to take the information that was provided to give us the information that we needed to seek out. If you know 1 or 2 of the values, you are likely able to figure out the rest of your values that you're being asked for. That is the end of this workshop. If there are still any questions on the content that was covered in this recording, absolutely reach out to the Math and Science Resource Center here at John Jay to get more assistance. You can book an appointment yourself through John Jay Navigate, or you can go to the Tutoring Center on campus, room 1.94 in the new building, and someone at the front desk can help you book an appointment. You can book one-on-ones, either in person or virtually, and there are plenty of tutors here who can help you understand the content better.